I hope this is gonna be the last video on glycolysis because we end up actually having around 4 or 5 videos, and it's gonna be the last video. So let's right away dive into this topic. So in this video and in this last video, we're gonna talk about the questions, right? And mostly about first diseases. We're gonna talk about why step 1, 3, and 10th are irreversible, right? And we can talk about regulations of this whole glycolysis. How can we regulate this? So let's dive into this. First, the most easy thing is understanding irreversibility, right? So why only step 1, 3, and 10 are irreversible, right? The answer is, I think, it's due to thermodynamics, right? Now, a lot of people will just memorize that irreversible enzymes, hexokinase, PFK, pyruvate kinase, but people don't ask why they are irreversible. Well, we have simple explanation for that. Imagine you are pushing a ball, right? And the ball barely moves. Now, the thing is, you can push it back easily. This is reversible reaction, right? If you can push it back easily, the reaction is reversible. Now, imagine the ball is rolling downhill, right? Can it come back itself? Can it come back uphill by itself? No. You would have to push it back uphill. That's an irreversible reaction right there. So cell works exactly the same way, right? That hill thing, right? This potential difference, right? It's called Gibbs free energy, right? So everything is revolving around this concept called Gibbs free energy. Okay, and we call it delta G, right? So that's Gibbs energy. Now, what is Gibbs energy, right? A lot of people will think that Gibbs energy should be less than, but let's build it, right? What nature does is actually, nature always move towards the nature, right? The nature moves towards what? Moves towards stability, right? So low free energy. Nature wants to move toward low free energy because nature wants stability in the system. Stability. That's very important, right? So basically, every reaction in this world is just asking that, will the products be more stable than the reactants? If the answer is yes, then the reaction can happen spontaneously. Okay, then reaction will happen because the products are achieving something which is called as stability, right? Now, to better understand this concept is that just imagine 2 rooms, right? So we have 2 rooms here. This is room A, this is room B, right there, right? Room A is super duper crowded, very hot, high pressure, right? So these particles are bumping into each other. Room B is like cool, empty, low pressure. Now the thing is, you open the door. Where do you think people will go? In room A or room B? Of course, room B, right? Not because they want to go to room B, not because they have choice, because it is a low energy state. The chemical reaction also behaves similarly, right? This delta G right here, right? It changes. Delta means changes, right? G means Gibbs free energy. Therefore, delta G means change in the free energy. Okay, so G is just free energy, right? Free energy. And delta means just change in free energy, right? So delta G changes in free energy. Delta means just change, okay? So delta G can be, first of all, it can have 3 types of changes, okay? Change number 1, delta G can be less than 0, okay? How? The products have less energy than the reactants, right? And the reaction move forward. It's called exergenic, okay? It's called exergonic, or whatever you call it. That's one possibility. Second possibility that can happen is that change in energy, or delta G, is more than 0, right? The products, right, have more free energy than the reactants, right? So this reaction is unfavorable. It requires energy as an input, okay? So we need energy in this, right? So does delta G more than 0 means the reaction is fast? No, absolutely opposite. No, not opposite. Absolutely different concept, okay? So if delta G is more than 0, it doesn't mean the reaction is going to be fast. These are like different concepts. Okay, so thermodynamics, right? Thermodynamics ask that should the reaction happen, and we use this change of energy, right? And we use kinetics, right? Kinetics is just how fast the reaction happens. Okay, so kinetics is just we use this activation energies, right? Enzymes effect, right? Enzymes, right? They affect these activation energy and not delta G, because delta G is just free energy, right? How can I explain it? Petrol, right? Petrol burning. Okay, so petrol is burning or gasoline is burning, right? Very favorable. Why? Because delta G is highly negative there. Should the gasoline burn? Yes. Right? Does it burn instantly sitting in your car? No, because it needs this activation energy, spark plug, right? So that's the concept, right? So enzymes, right? These enzymes that we have in this whole reactions, right? The question here is that do enzymes make reaction favorable? No, it doesn't. Enzymes don't make reaction favorable. Enzymes actually lower the activation energy. It increases the speed. That's it. It doesn't change any delta G or change any equilibrium, right? Enzymes of the whole reaction of this whole glycolysis, enzymes just lower the activation energy, right? That is required, right? So activation energy, and can increase the speed of the reaction, right? The PFK1, right? The rate limiting step, right? So why glycolysis uses irreversible steps? That's the first. I mean, why does it even happen, right? Why not every step? Why not make every step reversible? I already talked about it, because every road goes in both direction, right? No intersection, no traffic light. It's impossible to regulate this road, right? So instead, these major intersections have these traffic lights, right? So that's why the step 1, step 2, step 1, step 3, and step 10 are highly regulated. It's like you put traffic lights there so that you can regulate that, right? So step 1, we know that hexokinase, right? Step 1, hexokinase is there, glucokinase is there, right? Hexokinase is this high affinity, lower blood pressure, works nicely. Glucokinase, low affinity, works great at high blood sugar levels, present at liver and pancreas, where hexokinase present is everywhere, right? So hexokinase, the reaction is that when glucose changes into glucose 6-phosphate, right? Now this is irreversible again, right? Because actually it isn't glucose phosphorylation alone. The cell couples it with ATP hydrolysis, right? Now ATP is been broken down into ADP here in this whole in this step 1. That releases a lot of energy, and the combined reaction has a lot of negative gives energy, negative delta give. Okay, so therefore the product are much more stable. This reaction here, glucose is broken down, right? Not broken down, it's just phosphorylation, right? And the glucose 6-phosphate is much more stable, right? So another question can come to your mind that, it came to my mind that why can't glucose simply just become glucose again, right? It can, but not through hexokinase, right? That's a different enzyme. This becomes important, I think, in gluconeogenesis, right? It can be, but hexokinase doesn't do this, right? Step 3, we have this PFK enzyme, right? That's a step rate limiting again. We have ATP hydrolysis, right? Again, we are breaking down stuff, right? Large negative delta G, right? Irreversible stuff. Now, again, we have this PFK, right? And so the whole concept about irreversibility and reversibility is about change in delta, okay? Change in delta, that's very important. So deep question, we can think about these stuffs, right? But I think it's enough to put some idea about it, I think. Right? Okay, so PFK, right? Let's talk about PFK. PFK, phosphofructokinase 1, right? It's the main regulator enzyme, right? Suppose the cell has plenty of ATP, right? Already is full of ATP. What will happen? Should it continue breaking the glucose? Of course not, because it's wasteful, right? PFK slows down. Suppose ATP is low and AMP rises, right? So PFK is gonna speed up because we need ATP, right? So we'll study this in the regulation question that I just, this regulation question I had. We'll study this, how this regulation shit happens, right? Let's talk about PEP to pyruvate. That's done by pyruvate kinase, right? So reaction is PEP turns into pyruvate, right? PEP. Now, why is PEP so special, right? Because PEP contains one of the highest energy phosphate bonds in metabolism, right? Now, think of this PEP as like a big rubber band. Super duper unstable, releases a lot of energy, and PEP behaves similarly, right? Now, why ATP? Why we get ATP, right? You can ask me this question. Shashwat, why are we getting ATP? From where we are getting ATP, right? PEP transfers phosphate, okay, to ADP. That's what happening here, right? So when you transfer phosphate to ADP and then you change ADP into ATP, right? That's how you get ATP, okay? So why does this happen spontaneously? Again, same spontaneous question. Again, reversibility question. Why it happens spontaneously? Because pyruvate is much more stable than PEP. The reaction is happening downhill from higher energy state to lower energy state, and we are getting the energy in the form of ATP, right? So then you can ask me why pyruvate is so stable. I mean, it's just an assumption. I've told you, okay, pyruvate is super duper stable, but you can ask me this. Why pyruvate is so stable? Because immediately after phosphate leaves, the pyruvate undergoes into this thing called ketoenol tautomerization, right? Now it looks super duper scary, like sounds scary, but it's not. PEP first forms enol pyruvate, right? We have this step 9, right? We have this enolase, right? So here what's going to happen? Let's talk about this step 10 a little bit deeply, okay? So here what really going to happen is that, so PEP actually will form, first it will form something known as enol pyruvate, okay? Right. Now this stuff is like super duper high energy and it's not very stable. Immediately it will rearrange itself into something called as ketopyruvate, okay. So now this keto thing, right, this ketopyruvate is much more stable than enol pyruvate, and it's more stable than PEP itself, right? The keto form is much more stable. That extra stabilization makes the step 10, this last step, right, strongly irreversible, right? I don't know if someone will test you on this or not, but it's better to understand it than not understanding it, okay? So why are other steps reversible then? You can ask me, Shashwat, right? Shashwat, why are other steps so reversible, I mean, these 3 steps, I get it. They are irreversible because we are changing the product from highly unstable to a stable product. So it's happening spontaneously. What about these red, things? Read these. What about these steps? Step 2, step 4, step 5, right? Why are these steps reversible? Okay, let's talk step by step, okay? Here on the step 2, we are changing G6P, right? This molecule into something which is called as F6P. That is this molecule. Okay, let me color this again because it's not colored. Okay, so we are changing this thing, right? And if I'm saying that it's reversible, I mean, then you should ask me, Shashwat, why is it even reversible? Because no ATP is used, no ATP is made, a little energy difference. G6P and F16P, right? Sorry, fructose. Oh wow, I just made a blunder. Step 2 is when you convert G6P into fructose 6-phosphate, okay? Not fructose 1,6-bisphosphate. Okay, I'm so sorry. Okay, so that's the thing. So the concept here is that G6P and fructose 6-phosphate are not much different in terms of energy, okay? Very little energy difference. Enzyme simply follow the concentrations, okay? So same thing happens in step 5 here at DHAP and G3P, right? Both of them have similar concentration of energy. So the reaction can shift easily. This flexibility is important because metabolism constantly changes, okay? Right? That's the thing. Then I don't know if you know about gluconeogenesis, but gluconeogenesis cannot simply reverse glycolysis. That's a huge thing. I used to think that if we are just what is gluconeogenesis? Gluconeogenesis is making carb from non-carbohydrate sources. That's gluconeogenesis in simple terms. So I thought that why not the body can just take this pyruvate, right, and then do the whole reverse reaction from step 10 to step 1. We can call it gluconeogenesis, right? No, because if glycolysis breaks the glucose, right, why not simply run it backward? I thought about it, and it turns out that these irreversible reaction cannot be reversed. That's why gluconeogenesis is a whole different reaction than glycolysis. Okay, that's the thing. It's like water is falling, right, from a waterfall, right? Water falls easily. Can it flow upward? No, you need a pump or you need a guy to carry this water, right? So gluconeogenesis uses different enzymes, right? The gluconeogenesis bypasses these step 1, step 3, and step 10, right? You'll learn it. Later you will learn it, right? Gluconeogenesis doesn't use hexokinase. It uses glucose 6-phosphatase. It removes the phosphate, right? It doesn't use PFK. Instead, it uses fructose 1,6 biphosphatase, again, removing that thing. Pyruvate kinase doesn't use pyruvate kinase gluconeogenesis. We use pyruvate carboxylase and PEB carboxy kinase, right? Notice that 3 irreversible reaction, the gluconeogenesis bypasses these 3 exactly. Okay. Now you would ask me, how would these pathways even how would you break the pathways, right? Suppose step 2 become irreversible. Let's just imagine this. Okay, let's imagine this. Let's close your eyes and imagine this, that G6P and fructose 6-phosphate, they cannot they gonna be irreversible. Let's just imagine that. The problem now is that glucose can never. Now the problem that occur if step 2 becomes irreversible is that glucose could never enter into glycogen or pentose now, because we know that G6P is standing right here. It's standing on this way that it can either become glycogen synthesis, glycolysis can go in there, it can also go in pentose. Depends upon where, depends upon the activation of PFK, right? Interaction of PFK. If PFK is there and it has enough ATP to activate, to interact with this Mr. Glucose 6, right? Then only it will go to glycolysis, right? But if this step 2 is irreversible and it 100%, you are sure that G6P is gonna become fructose 6, we are 100% sure that our choice of this G6P will be lowered, right? It will 100% go into just glycolysis pathway. Now glucose could never go into glycogen synthesis or pentose phosphate pathway. The metabolism becomes not so flexible now, right? It's not so flexible now. Like entropy actually goes down if you think about it in this way, right? Suppose step 10 becomes irreversible, right? Suppose step 10, right, becomes reversible. Sorry, opposite, right? Step 10 is irreversible. You can't reverse it because the products are way different. The Gibbs energy is way different. Suppose step 10 becomes reversible. All of a sudden, PEP and pyruvate, they are not so different products now, right? And what's going to happen now? The ATP generation will be not so much. You will not get much ATP. The pyruvate will be super unstable. You will not even harvest any energy from this step 10, because to harvest energy, you need to have irreversible reaction, right? I hope I'm able to build this thing in your mind about reversibility and irreversibility, right? What else can we talk about? Clinical connection of these irreversible reaction, right? Let's talk about pyruvate kinase deficiency, right? If you are deficient in pyruvate kinase, right, what's going to happen in your RBCs? Because RBCs don't have any mitochondria, right? So no mitochondria means no oxidative phosphorylation, right? So ATP is going to go down, right? You cannot compensate. Your ATP is going to go down. Your sodium potassium pumps are going to go down, and then you'll have hemolytic anemia. Why doesn't the liver do this immediately, right? Why doesn't liver die immediately if you have pyruvate kinase deficiency? Because liver has mitochondria, that's why. Liver has fatty acid oxidation, beta oxidation, alpha oxidation, right? And TCA cycle and many, different sources of ATP. Liver has many other sources, but RBCs don't. So the most important thing that you can take away from reversibility and irreversibility is that you don't have to memorize that 1 and 3 and 10 are irreversible. You just have to think that, remember their jobs, okay? The step 1 is to capture and trap the glucose and activate it. Step 3 is to commit the glucose using PFK1. You put one ATP inside the whole product, and then it becomes super duper committed, and it will only go to glycolysis. And step 10 is finally we are harvesting the ATP, right? Everything else becomes just simple if you think about it like that, okay? Simple. So pyruvate kinase efficiency, hemolysis. Pyruvate deficiency in liver cells, less affected because liver cells have mitochondria and I don't know, a dozen other ways to get the whole ATP, right? What I'm saying, in short, what I'm saying is that if the large negative delta G, that is Gibbs energy, is involved, yes, if you're getting a lot of energy from a reaction, it will 100% be irreversible, and the reaction will strongly favor the product. Irreversibility under physiological condition will happen, and we have these 3 control points in the whole glycolysis, that are step 1, step 3, and step 10. Everything else is reversible, and that fact itself allows nature to be flexible, right? It allows metabolic flexibility, right? Gluconeogenesis must bypass these step 1, step 3, and step 10 to make glucose again, okay? So that's the principle, right? The irreversible steps are not like special or I don't know, like something, I don't know, insane. They just have different chemistry, right? They're special because they have these large free changes, right? That's why. So that's my first topic, right? I talked about why the irreversibility happens, right? So let me just put it somewhere. Okay, so we learned about the irreversibility, right? Why it happens, right? Let's talk about regulations of the PFK, right? Okay, wow, it just got messed up. Okay, we have Gibbs energy, right? So wait, I hope you understood the really basics of reversibility and irreversibility. I think it's gonna take a lot of time to really master these things. It's not so difficult. I think it's not so difficult. So let's talk about regulation now, okay? How are we gonna, just think about it. Just close your mind. I mean, not close your mind. Close your eyes and think about how would you regulate this whole reaction. I mean, we know that PFK is the rate limiting enzyme, right? It decides the overall speed of the whole reaction. How would you regulate that, right? How would you think that, how can we talk to PFK? Oh, sorry. Okay, so regulation. How would you regulate it? Of course, we need some signals, right? How does the cell decide whether to speed up or slow down the glycolysis, right? Super duper important concept, no? A lot of people will think, oh, ATP inhibits, AMP activates, insulin activates, glucagon inhibit, but why? You know, why inulin? Why is that? Let's start by thinking, okay? So the first thing that I want you to do is I want you to imagine you are that cell. You're that cell. Right now you have 2 possibilities, right? You are looking at your destiny and now you have 2 possibilities. You're thinking, what can I do? I can break the glucose. So, I mean, I'm gonna get more ATP, right? So I have 2 options, right? So you are the cell. Let me write it down. You are cell, right? You have 2 possibilities right now in your destiny, right? You're gonna break more glucose, right? Break stuff and then get more ATP, increase the ATP, right? Increase the general ATP of the system. Or what you can do is actually you can stop the breaking of ATP, right? You can not break, right? Stop it. Stop the glycolysis and save the glucose, right? Increase the glucose level, basically, right? Because if you don't stop, the glucose level is gonna go down, right? So the question here is that how will you know that which one to choose? How will you know, right? I think this question actually, it's more about how to measure your own energy state, right? Rather than asking what to do, you should ask yourself, the real question is, how do I, as a cell, how do I know how much free energy do I really got? That's the real question. right? So the cell has energy meters. Think about it. We have these things, right? Now think about your even laptop or maybe tablet or I don't know phone, right? At 100%, you don't need the charger. At 5%, you're like, oh my god, let's put the charger in, right? Immediately you put the charger, right? So cells have same kind of idea, right? How would I answer that? I would answer that these 3 meters. The first meter is called ATP meter. Second meter is called ADP meter. And lastly, the third meter is called AMP meter, right? Note you will understand that all 3 of them differ by each other with 1 phosphate, okay? It has 3 phosphate here, this has 2, and this has just 1. That's why mono, okay? Okay, so now you know this. So what is ATP here? How would you understand ATP? ATP here, high ATP means I have a lot of energy, right? Now think about it naturally. Will the glycolysis continue? Of course not, because you're already full on ATP. Why would you want to waste the glucose, right? Therefore, high ATP stops, right? So high ATP stops the process, stops the glycolysis, okay? What about other things? AMP, right? It's like, AMP is like 20%, okay? So AMP is like red. What's gonna happen? Oh my God, you need energy. Of course, you will start the process, right? Right? So first thing, basic question, where do ADP even comes from, right? Where do ADP comes from? Where do AMP come from? All of them, they come from ATP itself, right? ATP loses 1 phosphate, becomes ADP. ADP loses 1 phosphate, becomes AMP. So when ATP is consumed fast, AMP becomes to rise, right? It's like meter, right? Right? So AMP rises, and you're thinking, oh my God, I'm low on battery. I need energy. I need fuel, right? So AMP is the signal that cell is running out of energy, right? So therefore, of course, increase the damn process, right? Start, right? So that's the thing. Just start the glycolysis, right? Now, why doesn't ATP activate glycolysis? ATP, right? Why doesn't? I mean, I hope you understand that, right? ATP is just, you already have the juice to work. Then why would you want to work overtime? For what, right? You already have. But imagine you just have 2. I don't know. You don't have any energy. You're like, I'm tired. I need some energy. Okay, let's hunt for energy. So then you check your AMP, and AMP is like rising. Oh my God. So of course, now you're gonna start the whole glycolysis process, right? So the most important enzyme in this whole thing, I mean, not in this whole thing, the most important enzyme here is first is PFK, okay? The PFK, step number 3, okay? So major checkpoint is PFK. Why regulate PFK instead of other enzymes, right? Why would you want to regulate this only? Why would you only this PFK? Why? Because how would I answer that? PFK is like entry to the glycolysis, okay? So if you regulate the entry, the whole glycolysis is quite nicely regulated, right? So ATP inhibits PFK, right? Because energy abundant right now, right? Why keep breaking glucose? No reason, right? So therefore ATP binds to PFK, the enzyme activity decreases, and glycolysis slow down. So that's the thing. Stops the whole process, right? Now I want you to notice this thing, right? ATP now has 2 things. The first thing is ATP can act as a substrate, right? PFK needs ATP to phosphorylate, right? PFK needs it, right? This PFK, right? It needs ATP, okay, to interact, right? PFK needs this to phosphorylate fructose 6 phosphate, right? It needs to interact with what? With fructose 6 phosphate, okay? It's needed. That's how it's gonna put the phosphate, right? So that's first job. Second job, it can also act as a regulator, the ATP, right? So when ATP concentration is much higher, it binds to a different regulatory site now. And PFK changes the shape. It's so insane how it happens. But now PFK is gonna work very slowly. And this thing is called allosteric regulation, okay? So when PFK is stopped, right, we call this thing as allosteric Static regulation. Wow, Shashwat, you're just throwing new words here and there. What does it even mean? Yeah. What does allosteric means? Allo means other, first of all. Allo means other. Okay. Steric means shape. So allosteric means other shape. Okay. Meaning, what does it mean? It means that molecule binds somewhere else, right, other than the active site. This changes the enzyme shape. So allosteric means different shape, right? Simply, the molecule binds somewhere other than the active site. Simply, this changes the shape of the PFK. Okay, so that's how it happens, right? What about AMP, the low energy stat, right? So we have AMP. AMP actually activates the PFK1, right? It activates, starts the PFK. AMP tells the cell, hey, we are running out of ATP, therefore speed up the PFK, right? More glycolysis, more ATP, right? Once we have enough ATP, the negative feedback starts, and that's how it works, right? What about citrate, Shashwat? Have you even heard about citrate? Yeah, I have heard about citrate. What is citrate? Okay, let me write citrate, right? Citrate. Okay. So that's a citrate. I just made that. Now, what is a citrate? We will study citrate in TCA cycle. For now, just know that high citrate means the mitochondria has already a lot of fuel. Okay, citrate is fuel of Mr. Mitochondria. Okay, so if citrates are full, of course, should the glycolysis continue? No. Why not? Why do you want to waste the glucose? Glucose is such a luxury, right? So citrate also negatively, of course, not negatively, positively, I mean, also inhibits PFK, right? Think of citrate as a message from mitochondria like, oh, we have enough fuel, stop your glycolysis, stop wasting the glucose, right? Okay, so what about other molecules such as fructose, right? Fructose 2,6-bisphosphate. Let me write it up. Let me write it here. We have this molecule called fructose 2,6-bisphosphate, right? Right there we have that. So we can call it as F2,6BP. Okay. So we have this, one of the coolest molecule in metabolism, right? A lot of people will think, oh, it's just, where's the one? Well, one is not there, it's two. It's different molecule now, right? First question, why does F2,6BP, this fructose 2,6-bisphosphate, even exist? Why? Just to mess you up? No. If ATP, now listen to me close. If ATP and AMP already regulate glycolysis, why create other regulator? Why would you want to do that? Now I just gave you a hint. So it means that F2,6BP is a regulator. Are you saying this? Yes, I'm saying this. But why would you want to create another regulator? Because ATP reflects cellular energy and F2,6BP regulates whole body hormonal status. That's the difference. They are kind of two different types of regulators. So it's a different regulator. ATP works on a cellular level. Okay. F2,6BP works on a whole body level. Okay. Now let me answer more. Okay. ATP tells you how much energy is there in the cell. Insulin tells you how much glucose is there in your whole body, right? Different question, different regulators, different answers. F2,6BP activates PFK, right? It positive. It activates it, right? Now it's a statement, right? I just gave you assumption, right? Now it activates it. It means F2,6BP is a sign of low energy, right? Now, when should glycolysis increase? Think about it. Just close your eyes. Why? When? Before the meal or after the meal, right? Glycolysis happens because glucose is available, right? When are you gonna have glucose? Before the meal or after the meal? What do you think? Of course, after the meal. After the meal, you'll have glucose, right? After eating, the glucose rises. Insulin rises. Cell should use glucose. Therefore, insulin leads to increased levels of F2-6 BP. Right? So let me write it. Insulin. Right? And eating. Postprandial, or I should say after eating. After eating, right? So that's what happens. Okay? So F2-6 BP, insulin, and eating, right? It increases what? PFK1. Okay? So PFK1 is now activated and we will have fast glycolysis. Increase glycolysis. Okay? So that's happened. What about glucagon then? What do you think about glucagon, Mr. Avasthi? What do you think about it? Well, I don't think anything about it. I just know that it's a cool character. Glucagon. When glucose is gone, I'm gonna do things. I think about glucagon like this. Okay. So what happens when you don't eat, right? Imagine you didn't eat for 10 hours. 10 hours, not much. 12 hours, let's see. Right? Fasting. You are fasting, right? No insulin. What's going to happen if you don't have insulin? The glucagon will rise now. It's the opposite of insulin. So increase glucagon. Because glucose is gone. Right? So during fasting, during fasting, right? You're fasting. Glucagon rises, right? That's a assumption right there. I'm going to tell you why even. So glucagon does the opposite thing, right? During fasting, let me ask you a question. Should the liver consume the glucose? You're fasting, You're like, I don't have enough food. Your body needs food to move, You're going to be depressed if your brain goes low on sugar. So what do you think? Brain needs it, by the way. Brain needs free sugar. So what do you think? Liver will cop the glucose or not? Absolutely not. Liver is going to spare that glucose, right? So liver is going to leave it. Liver is going to be like, okay, brain, I think you're more important than me, I guess. So therefore glucose, right? Glucose is redirected to the brain when you're fasting, right? So therefore glucagon rises, right? F2-6 BP is gonna what? Positively influence or negatively? Of course, negatively. So glucagon is gonna negatively influence what? PFK as well, right? So it doesn't happen like this. It happens actually like this. It doesn't interact directly with PFK. It happens like this, right? Right there, negatively. So glucagon, fructose 2,6 bisphosphate falls. So PFK also is stops. So liver glycolysis slows down. So what's gonna happen if glycolysis is gonna go down? We know that if glycolysis goes up, right? If we are not breaking the glucose, what are we doing? If we are not breaking it, we are building it. So what's gonna go up? Gluconeogenesis is gonna go up. Okay. I hope you can know that or understand that. Gluconeogenesis is that when you build up glucose from a non-carb source. So what's going to increase? Gluconeogenesis. Right? So notice something, right? You notice something. The regulation is super duper important in liver, right? This glucagon and this whole regulation is super duper important, right? Because liver has to now think that should I do glycolysis or should I do gluconeogenesis? And everything depends upon your fasting and not fasting, and then glucagon and insulin, right? Now, why does insulin stimulates glycolysis? You can think so, right? Why does insulin stimulate fructose 6 biphosphate, right? Imagine you just ate, right? Your blood sugar right now, or blood glucose right now is 90. You just ate, and now you just had a big meal, and start like right away your blood sugar is gonna be 150, right? What's gonna happen? Pancreatic beta cells are gonna be like, oh my god, that's a lot of sugar. So blood 2 transporters are there at the pancreatic beta cells. Insulin is gonna be released. Cell is gonna take up all the glucose, especially muscles and fat, right? Liver stores of glucose, right? Liver stores the glucose. Liver is also gonna take that and gonna start metabolizing. Oh my god, metabolizing it, right? Metabolizes it. Okay, liver stores glucose and metabolizes it. Okay, so glycolysis actually increases when you have a big meal, right? Because you have glucose. How will you even do glycolysis if you don't have glucose? That's why drinking energy drinks, consuming glucose increases glycolysis. Glycolysis is just breaking down that glucose, right? No, okay. What about glucagon? Glucagon stops liver, right? Stops the liver glycolysis, right? Now imagine you're fasting overnight, you don't eat anything. Blood sugar is like falling. Now, should the liver burn its remaining glucose? What do you think? Or it should produce glucose? Glucagon shifts metabolism towards gluconeogenesis and away from glycolysis. Okay, so that's important. When you're fasting, your blood sugar, liver wants to maintain the blood sugar. So glucagon increases. Liver is like, okay, let me increase this gluconeogenesis because this guy hasn't had anything to eat in last 12 hours, right? Need to maintain this blood sugar. His brain needs to work. That's important, right? Okay, some clinical things. What can we think? Why does the diabetes affects glycolysis? Okay, you have diabetes. Let's say you have type 1 diabetes, okay? What happens in type 1 diabetes? So, type 1 diabetes you have, okay? Type 1 diabetes. You have less insulin right now. What's going to happen if you have less insulin? If you have less insulin, you'll have less F26BP. Yes, less activation of glycolysis in insulin responsive tissues, right? So liver is gonna be like, okay, I guess he is not eating well. I need to start gluconeogenesis because his blood sugar is not rising, right? So liver continues producing glucose, and then we have even more hyperglycemia, right? Because low insulin actually goes to this pathway. Low insulin means no insulin. It doesn't mean, but kind of works like that, So that's type 1 diabetes. What about working out, right? You're working out. What happens when you are like sprinting? ATP is gonna, ATP is gonna fall and AMP is gonna rise. Once the AMP rise, what's gonna start? PFK is gonna start like, okay, we don't have enough ATP. Gotta start glycolysis. And the thing is, glycolysis is super duper fast. It's very fast. It's super duper inefficient way of making energy, right? Because mitochondria makes, I think, like 30 ATPs, but this shit makes like 4. Okay, so but still, our body is like, okay, I don't care about efficiency right now because we need energy. We need it fast. This guy is running away from a lion. He needs not to die, right? So you're running, ATP falls, AMP rises, PFK activated, glycolysis accelerated, super duper, and this allows ATP production to go up again, right? Now, again, energy drinks. Let's come back to the energy drink. You drink that energy, you have that glucose, insulin shoots up. What happens when your insulin shoots up? When you have high insulin, you have F6BP. When F6BP goes up, you have what? PFK is positively influenced, PFK goes up, glycolysis goes up, right? Okay. Someone can ask you, hey, mister, you just had this energy drink. Which irreversible which irreversible enzyme is going to go up? Of course, Mr. Pyruvate kinase. Okay. What can we think? Let's break the regulators. Let's try to break these things, right? Let's try to break insulin. Let's try to break F26BP, right? Imagine ATP could not stop PFK1. Suppose ATP, right? Suppose the ATP cannot do allosteric regulation. Just imagine, suppose. Now what happens? The cell is going to continue burning the glucose because the cell will not be able to understand this decision, this thing that how much do I really have, right? So even when the ATP is like abundant, we gonna have a wasteful glucose. The glycogen stores will disappear, right? The person will be tired, really tired. Okay, let's talk about AMP. Suppose AMP is failing, right? Okay, AMP couldn't activate PFK. You're working out, your AMP levels are rising, and ATP is falling, and AMP is rising. But due to some hormonal problem or some genetic problem, you have a shitty AMP. What's gonna happen? The cell will not increase glycolysis. You will have energy crisis. So there are a lot of questions then they can ask you like, hey, this guy was working out for I think like 10 minutes and he feels like he's gonna die. And he has to drink something sweet. He has a shitty AMP, you know. Suppose let's break insulin. Suppose insulin couldn't activate glycolysis. Suppose insulin cannot or doesn't know how to talk to F26BP. So this is exactly what happens in diabetes, essentially. Glucose remains in the blood, but cell cannot use it effectively. We will have just hypoglycemia, and then we can have a lot of other things, right? Suppose glucagon doesn't talk to liver. Suppose glucagon couldn't inhibit liver glycolysis, right? Suppose glucagon doesn't stop F26BP. What's going to happen? So during fasting, your liver will think, okay, this guy is not fasting, because essentially liver cannot think. Liver just have to check the glucagon and insulin levels, right? Liver is like, okay, this guy insulin is high. I guess he just ate, but in reality, you were sleeping for like last 12 hours, right? I don't know why were you sleeping for last 12 hours, but you were sleeping for last 12 hours, and your liver is like, oh my god, I need to do something. He just ate a big meal, right? So no gluconeogenesis. Your liver is gonna burn all the precious glucose. You will have a big hypoglycemia, maybe coma, right? So the regulator is just ATP increases, AMP, okay, ATP, more ATP means energy, enough energy, right? More AMP, it means you're tired, you don't have energy, so low energy. Increased citrate means the fuel from, right, increased citrate is just TCA cycle well working, like well supplied, right? So again, negatively stops PFK. Insulin, fed state, I need to do glycolysis, need to break down this whole thing, right? So eating increases fructose bisphosphate, right? What about insulin? What about glucagon? Well, you didn't eat, you were fasting. So I guess we need to increase the blood sugar a little bit. How would you do that? You would do that by gluconeogenesis, right? What about fructose 2,6-BP, right? Bisphosphate, right? So what's going to happen? Of course, it positively influences, right? It increases PFK, right? So maybe a question will say, a marathon runner running, right, reaches the final mile, right? And what's going to happen? ATP is going to go down in this guy, right? AMP is going to go up, PFK is going to go up because AMP is up, glycolysis is going to go up because he needs energy, right? Now, if the question says patient just ate super duper big bowl of rice, what's going to happen? Glucose is going to shoot up, insulin is going to shoot up, F26BP going to shoot up, PFK going to shoot up because you need to catalyze, you need to break down this glucose just because this guy just had a big ball of rice, right? And imagine if the question says overnight fasting is happening in this guy, what's going to happen? Well, glucagon, first of all, going to go up because insulin is low, right? F26BP is going to go down because the glucagon is high, right? Glucagon is, it inhibits F26BP, right? And what about PFK? PFK1 is also going to go down because F26BP is less. And gluconeogenesis is going to happen because liver wants to maintain your blood sugar, right? You didn't eat for 12 hours. You were fasting. So that's the regulation. Oh, wow. Okay, so that's it, you know, that's it. The overall principle is that you again, the cell has to think, how do I know how much energy I have, right? Should I break more glucose and increase the ATP, or should I stop the glucose and save the glucose, right? And how would you know that? You would know that by ATP, by AMP, right? By fructose bisphosphate, by insulin, by glucose, right? That's how you would know. So that was regulation, right? That's how you kind of regulate the whole uh, glycolysis. How would you break the glycogen or glucose? Okay, what a nice concept and topic, right? I love it. Okay, let me color it down a little bit. Let's go to the next topic right away. Don't want to make another video. Okay, kind of done. Yeah, looks bad. Yeah, I know it's not perfect, but who cares? Perfect. Let's talk about medicine now. Diseases. Okay, let's talk about diseases. Okay. So this diseases is essentially, we are just asking, what if these step 1, step 2, step 3, step 4, step 5, step 6, blah 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 goes wrong? Okay, what if the steps go wrong? That's what we are asking essentially, right? Until now we studied normal, glycolysis, right? Now we're gonna answer a different question. What happens when one glycolytic enzyme goes down or goes fail or goes bad or goes rogue? Not rogue, right? So we have bunch of diseases. First of all, hemolytic anemia, diabetes, cancer, alcoholism, poisoning, right? A lot of things. The best way to really think about these diseases is that every glycolytic disease can be understood by asking these 3 questions. Okay, best way. This is the best way. First thing is that you want to locate the enzyme. Which enzyme is being affected? Second is that you want to understand what is being accumulated, right? And the third thing you want to ask is what is no longer produced, right? So first thing is that which enzyme is the one that's messed up, okay? Locate the enzyme. Second is just before the enzyme, what is being accumulated? Accumulated, right? What is being accumulated? And the third thing is that which product is going down, what is no longer produced, okay? The product. All right. We now ask ourselves, right? Which product is no longer produced, right? Produced. So we have essentially 3 questions, right? First is which enzyme, second is what is being accumulated, and third is what product is no longer produced, okay? That's how you can just understand everything, okay? So disease 1, pyruvate kinase deficiency. Which enzyme? What do you think? Which enzyme? First question, even before I know asking, let's locate the enzyme, pyruvate kinase. Where? Step 10. Let's go to the step 10. There's the step 10. Pyruvate kinase deficiency. Okay? What's happening here? We have a deficiency. We don't have this enzyme. So where is pyruvate kinase? Step 10. PEP turns to pyruvate plus ATP with the help of this enzyme called pyruvate kinase. Okay? Let me just put it here. He's sitting right here. Okay? So, question. What is lost in this enzyme? Right? What is lost if the enzyme is failed? What is lost? We lose a lot of ATP, bro. That's what we lose. All right? So first disease. Pyruvate kinase deficiency. What happens if we have this deficiency? What is being not produced? ATP is not being produced, right? ATP is the goal of glycolysis, right? Not pyruvate. It's very important, right? Clinical problem is ATP, not pyruvate. Why the RBC is affected? Because of ATP, okay? It's very important, right? Because these RBCs don't have mitochondria. If glycolysis fails, the RBCs will eventually die, right? RBCs cannot produce ATP without glycolysis. Therefore, they're gonna die, right? Why does ATP matter? You can ask me, right? Okay, let's even ask a more basic question. What does an RBC need ATP for, right? Or why does an RBC need ATP? I mean, we know that RBC is not dividing. Yeah, it doesn't have any DNA, right? I mean, it doesn't have that machinery to divide, right? It doesn't synthesize DNA, right? So why ATP? Because ATP actually powers what? Potassium slash sodium potassium pumps called ATPases. They use ATP as the main fuel, right? This pump constantly maintain the low Na concentration and high potassium concentration intracellularly, right? Without ATP, these pumps gonna fail. What happens next? ATP fails, Na is gonna accumulate, right? What's gonna happen if Na goes up? If they fail, right? Na goes up, so water will follow. Swell, the cell will swell. All right, membrane becomes super duper rigid. So the splenic macrophages in the spleen, right? They remove these abnormal RBCs, and you're gonna have hemolysis, right? And you're gonna have hemolytic anemia, right? So spleen is like remove these weird big fatty RBCs, and then hemolytic anemia. Okay, that's first disease, right? How would this patient present? The patient will present as fatigue, right? Pallor, jaundice because we are basically dying, like RBC is dying, right? Splenomegaly, that's very important actually. So megaly, we will see megaly right there. Very important right there, right? Question, why jaundice? Because destroyed RBCs have hemoglobin, right? Heme degraded bilirubin. Bilirubin is gonna give you this. Gonna give you just unconjugated hyperbilirubinemia, right? Unconjugated means not soluble. Conjugated means soluble in water, okay? Lipophilic, I should say. Better word is lipophilic for unconjugated, okay? Pyruvate kinase deficiency causes this chronic hemolytic anemia, okay? So not because pyruvate is absent, it's because ATP is down, okay? And pyruvate doesn't have to do much, okay, with this disease. Second disease was what we can have is we have this hexokinase enzyme, right? Remember, it's the enzyme that is irreversible and it does all the trapping, right? You have this deficiency. What's going to happen? What happens if we don't have this enzyme? We don't have enzyme. Imagine you have deficiency of this. What happens if glycolysis cannot even begin, right? Glucose cannot enter, glucose cannot become glucose 6-phosphate, glucose is entrapped, entire pathway slows down, ATP goes down, again RBCs is gonna be super duper vulnerable. RBCs are vulnerable. It's a risk factor, right? Favorite disease. Next, cancer. It's not my favorite, but I mean, it's super duper interesting to learn about it. So cancer, what happens in cancer? Why am I even talking about cancer? We have something called as Warburg effect. Warburg. Warburg effect. Okay, so that's the thing we have. Warburg effect. Oh, what is it, Warburg? Right. It's super duper amazing. Question here is that cancer cells have oxygen. Yes, cancer cells have oxygen, of course. But still, cancer still perform lots of glycolysis. Now, you must think, wow, that's so stupid, no? When this effect is called Warburg effect, that cancer prefers glycolysis rather than oxygen, aerobic glycolysis, right? Rather than using oxygen, right? Cancer likes anaerobic conditions. Cancer preferentially uses glycolysis even in the presence of oxygen. This is insane, right? We call it aerobic glycolysis. Even if this cancer has oxygen, he will still do aerobic glycolysis. Yeah? Cool stuff right there. Why? Why would it happen? Right? Why wouldn't oxidative phosphorylation, right, using mitochondria and blah blah blah, produce much more ATP? Yes, of course, because oxidative phosphorylation makes like 30 or 32 ATP, right, per glucose. Here, per glucose, we just make 2, right? So why? Cancer cell doesn't care about efficiency. Cancer cell care about speed, and that's why when you're working out or exercising, glycolysis shoots up. That's why. So glycolysis provides rapid ATP provides fast nucleotide synthesis, right? Provide not fast nucleotide synthesis, produce rapid ATP. So cancer is actually building new cells, right? It needs this lipid, it needs amino acid, it needs nucleotide, these ATGC blocks, right? It needs this, right? And that's why we actually do this thing called FDG PET scan. That's the reason. Because cancer uses this glycolysis, and we actually use this. So remember, FDG PET. Let's go back to our old class, right? Old part. Here, where is Mr. FDG? Where are you? Where did I write you? FDG. Constant food, Arabic. Okay, I don't remember. Where did I even write it? Okay, never mind. It's okay. I'll write it again. FDG, right? Cancer cell uses a lot of FDG, right? Cancer cells does a lot of glycolysis, right? So what happens is that in cancer, the glycolysis increases, so glucose uptake increases. More FDG gets trapped, right? And tumor appears bright. That's how we use it. That's it. Next disease. Next disease is diabetes. I mean, we already talked about it, right? Let's talk about diabetes. Type 1. Let's talk about type 1. What's happening? No insulin or less insulin. What's happened if you don't have insulin? Reduced. It's reduced. What reduced? Less insulin. Okay, first of all, what's going to happen if you don't have enough insulin? You'll have less glycolysis, because the glucose will not shift inside the cell. It will just stay in the blood, right? So less glycolysis, right? Liver is thinking, wow, we have really less glucose. I need to raise the glucose levels. This guy has not eating, right? So liver is like, okay, let me just do neogenesis. So liver will shift to neogenesis, and even more hyperglycemia is gonna be there. Hyperglycemia, right? So that's happened. Now the problem here is not glycolysis itself. The problem is Mr. Insulin, right? That's the problem. Okay, other disease, alcohol. What happens in alcohol? What do you think? Why does alcohol affect glucose metabolism at all? Right? This becomes much more clear after we study ethanol, right? But for now, just remember that alcohol, don't want to go into whole ethanol because it will take another 6 hours, maybe, I don't know. So what happened is that alcohol actually increases levels of something which is called NADH. Now we know that NADH, right? We know that NAD plus, when you put one electron or hydrogen on this, right? When you add a hydrogen, it becomes NADH, right? We know that already because we studied this already, right? Now, why increase NADH is a problem? Why would that be a problem? Well, turns out that if you have, so why excess NADH is a problem? Because a lot of metabolic reactions, they need NAD plus, right? Especially our step 6. Our step 6 needs NAD plus because it's gonna remove this H plus, right? Remove that H plus, and then I'll put that H plus on NAD plus, right? So it needs that NAD plus, right? If you don't have enough NAD plus, right? Now, many metabolic reaction requires this NAD plus. If NADH very high, NAD falls, right? It's like how would you say, ATP and AMP situation, right? We know that if ATP goes up, AMP goes down. Same situation with NADH and NAD plus. If NADH goes up, then we will have NAD less. And we have, if we have less free taxi for the electron, for the hydrogen, then the reaction will not take place basically, right? Because this is a reversible reaction again, right? The step 6 is a reversible. So not a lot of energy gradient there, right? So this whole thing will not. Actually, what can actually happen is that we can have a reverse reaction, right? That's the thing. If you increase the NADH right there, and if you increase NADH levels, we can actually reverse the reaction, right? So GAPDH, this step 6 reaction, right? This reaction, step 6, GAPDH, right, requires NAD plus, right? Without enough NAD plus, glycolysis slows down, right? And even if the NAD plus is like, if it's a lot, then we can even reverse it. So that's the problem. So alcohol actually messes with step 6. Okay, what about other disease? Arsenic, right? Arsenic, ARSENIC, arsenic poisoning, right? Now, which glycolytic enzyme are we talking about when we talk about arsenic, right? We are talking about GAPDH. Normally, we know that this step 6 GAPDH enzyme, this glycerol-aldehyde 3-phosphate dehydrogenase, means it removes it, right? It removes the hydrogen from G3P, right? And it puts that hydrogen into NADH, right? And then we get 1,3-BPG and NADH, right? Now, arsenate can substitute for phosphate, right? And the product becomes super duper unstable. ATP generation is, just bypassed. So energy is lost. So even though glycolysis continue, ATP production will fall, right? Because phosphate is the currency of energy. Okay, arsenate can just replace phosphate. Okay, replaces phosphate. If you replace the phosphate, you will essentially not generate any ATP. Okay, the energy will be lost, even though the glycolysis will happen, but you will not get ATP, right? Now, why is this dangerous? Because cell loses energy despite a good glycolysis happening, right? Okay, what about fluoride, right? Where is fluoride? We have seventh disease. We have seventh disease, fluoride. Mr. Fluoride, FLORIDE, fluoride, right there. Okay, we talked about it already actually, fluoride, right? About tubes, right? Here on the step 9. So step 9, we have this enzyme called enolase. What it does is actually it breaks down the 2PG, removes the water, and we get PEP. And then PEP in step 10 can be converted to pyruvate, and we get ATP, right? So 2PG, that's the thing. This fluoride can stop enolase. And why would you want to do that, right? We want to do that because suppose blood is sitting in a lab, right? RBC is still gobbling that glycolysis, doing this glycolysis, eating the sugar. So sugar concentration is going to go down. So lab will falsely report hypoglycemia. Fluoride stops this enolase. So glycolysis shows, right? And glycolysis slows down, right? So the glucose level is actually much more accurate if we use fluoride tubes, okay? What about exercising? Well, exercising again, why can sprinting continue for several seconds despite limited oxygen, right? Why can sprinting, that's like running fast, continue for several seconds despite we have less oxygen, right? Because glycolysis shoots up, and we will have fast ATP, and that's how even cancer abuses this glycolysis, right? And that's how we use FDG PET scan. Okay, let's break these concepts a little bit more. What if RBCs had mitochondria? Just imagine that. Now, if RBCs had mitochondria, the pyruvate deficiency would be much less severe, right? Because RBC would just compensate by oxidative phosphorylation, right? But they don't. How can we break the cancer concept? Okay, what if our cancer relied only on oxidative phosphorylation, right? Cancer growth will be slower, much slower. What if fluoride never inhibited enolase? Well, I guess we will still have falsely diagnosed hypoglycemia, right? So that's the thing. So if someone asks you chronic hypoglycemia, chronic hemolytic anemia, you should think about pyruvate kinase deficiency. If they say PET scan is going to go up, Warburg effect, of course. If they say blood glucose tube contains fluoride, it means it's inhibiting something which is called as enolase. If the question says arsenic poisoning, well, I guess we are replacing phosphate, and then we will not generate ATP despite the ongoing glycolytic reactions, right? So that's the concept right there. So let's try to integrate everything which I have been yapping for last 1 hour, right? Let's build the whole concept now from final integration, right? Let's build the entire glycolysis knowledge. We have learned that why glycolysis exists, right? In first two videos, we talked about it. We talked about every major step. We talked about every irreversible enzyme. We talked about regulation. We talked about these diseases, right? We talked about the how can someone ask you, right? Now we are going to connect everything into one framework, okay? And this is the part you make glycolysis super duper perfect, okay? Now imagine you're a cell. Close your eyes again. Someone gives you someone gives you one molecule of glucose. Question is, what is your overall objective? It's not to make ATP. The cell actually has 5 objectives now, okay? Okay, so you get a molecule of glucose. What you're gonna do with this, right? You actually have 5 objectives. Objective 1, you wanna keep the glucose inside. That's the first task. Trap the glucose by using hexokinase, right? First problem is how will I keep the fuel, right? That's very important. So step 1 is hexokinase, important. Objective number 2 is that you want to decide, after trapping that glucose, you want to take a decision whether to use it or not. That's also important, right? Should every glucose molecule immediately be burned? Should we do that? Sometimes glucose should become glycogen, right? Sometimes it should become ribose, pentose pathway. Sometimes it can go to glycolysis, right? This major decision actually is taken by whom? Mr. PFK, the star of whole gang, right? PFK. That's why PFK1 is called the committed step, right? Once PFK acts on, 110% the glucose will go in glycolysis. Now, once the glycolysis shifts inside this glycolysis pathway, glucose shifts inside this glycolysis pathway, step 3 is to split that glucose. Now, how would you do that? Right? Because glucose is a large molecule, 6 carbon, right? Because one large molecule is difficult to process, What you're gonna do? We're gonna break that, split that, right? Splitting. How would you do that? How would you break this? Aldose, Mr. Aldose, right? So Mr. Aldose, ALD, Mr. Aldose. Step 4, or I should say objective 4, is to capture that ATP, right? We capture ATP at 2 steps, step 7 and step 10, right? Step 7 is then when we do phosphoglycerate kinase. We have 1,3 BPG. We do this phosphorylation, right? We add a phosphate on ADP, we get ATP, right? So, okay, step 4 is energy hunt. How would you do that, right? Because mostly inside there is carbon and hydrogen amount, right? Cell doesn't release all the energy at once, but instead of that, it captures a little bit of energy on every step. For example, step 7, step 10, right? Some of it becomes ATP, some of it becomes NADH, right? And the last goal or objective, step 5 objective 5 will be to produce pyruvate. That's the least priority. The most highest priority is energy hunt. So pyruvate, right? 3 carbon. That's called pyruvate. 3 carbon, right? Pyruvate is the end, right? You must think so. Well, actually, it's not, because pyruvate is the beginning, and pyruvate is actually asking a question. Pyruvate is asking, now what? Now where should I go? Now where should I go, mister? That answer depends upon the availability of oxygen or not, okay? Right? Pyruvate, right? That pyruvate is asking, where should I go, right? That's the thing now. Pyruvate actually is a crossroad, right? Think of pyruvate as this crossroad, right? Many tracks leave it, many tracks. With oxygen, it will go into this TCA cycle, right? It will produce a lot of energy. Pyruvate is very high energy. It will produce like 30 to 32 ATP per glucose, right? So that's another pathway. Without oxygen, it will change into what? It will no oxygen. Let's just imagine no O2. What will happen to a pyruvate? Will have something called as lactate. You know, the burning in your pain. Now, why lactate? Not because lactate is useful or something, right? It's not because of that. It's because the main purpose is to regenerate or increase NAD plus, allowing glycolysis to continue, right? When oxygen is limited. Without NAD plus, the step 6, that is GAPDH, right? This step would fail, right? So that's the thing, right? Other pathways pyruvate can take is oxaloacetate, right? Alanine is just amino acid, right? So pyruvate is actually a metabolic hub of a lot of other pathways, right? So I don't want to jump in TCA because that'll be another 6 hours, right? No one want to jump. What about gluconeogenesis, right? When are you fasting? Should glycolysis happen? No, because why do you want to lower your blood sugar when you're fasting? Gluconeogenesis should become, right? Should happen. Remember, okay, whenever we will talk about glyconeogenesis, we will talk about glucose 6-phosphate, fructose 1,6-phosphate. I mean, these enzymes simply. So I guess we understand most of the glycolysis, right? Now, I hope you loved that series because I spent a lot of time really thinking about why and hows and why not, right? And that's how it should be. What about pentose pathway? Did I even tell you about anything? Pentose pathway. What is pentose pathway? Pentose pathway is just when cell needs this NADH, ribose for this DNA synthesis, right? Ribose is just sugar, right? Now, if cell needs this ribose for DNA, what do you think? Should glucose enter into glycolysis? Of course not. I mean, not necessarily, but I think it should not, because we wanna shift this glucose to producing DNA synthesis, right? So that's the thing. So the whole thing actually is simply glucose leads to hexokinase, then glucose 6-phosphate. Now from this glucose 6-phosphate depends upon PFK. If PFK is there and we have enough ATP, we will go into glycolysis. That's it, okay? Now, under what condition does glycolysis fail? That's the super quick question, right? Let's just challenge this pathway. Okay, under what condition glycolysis fails? When would it fail? It would fail when we don't have glucose. First of all, you're fasting, so it will fail in this, right? So fails when you're fasting, right? Fasting. When else it can fail? When we don't have ATP. That's also true. When we just worked out and we don't have any ATP, right? No ATP to start. Cannot phosphorylate the glucose, nothing. No investment phase, right? We have 2 phases of phase 1, that is investment. Phase 2, that's the payoff phase, right? The phase 1 fails, right? When it can fails more. When we don't have the taxi for the electrons, not for the electron, for the hydrogen. So less NAD plus. When? Alcoholism, right? You'll be tired. When? Pyruvate kinase deficiency, right? No, the final step fails, no ATP, right? What do you think? Will oxygen do anything? Does oxygen has a say in this reaction? Actually, no. Glycolysis continues because it's an anaerobic reaction. Don't need any oxygen, right? But the thing is that pyruvate needs oxygen for aerobic metabolism, right? So instead, what's gonna happen is that if we don't have enough oxygen, we will have lactate, right? Lactate production increases to regenerate this NAD plus. Okay, I'm not gonna talk about that now. What if you don't have mitochondria? Does your mitochondria have anything to say in glycolysis? Right? No mitochondria. What's gonna happen? Oxidative phosphorylation is gonna be impossible. Cell will just depend upon glycolysis. So glycolysis It has nothing to do with mitochondria, right? So that's the whole topic, brothers and sisters and friends and Romans, right? That's it. That's the whole concept of glycolysis in, I don't know, 5 or 6 videos. So take care. I hope you will love this glycolysis concept breakdown, like very slowly, which took me a lot of hours to just speak, like blah 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 blah. Right? Okay, so have a nice day. What am I even doing? Okay, let me just. Okay.